fact that so you have these two phases. One is the training phase, and the other one is the test phase. And during the training phase, you have a model and you have some data set. And then you use this data set to train the model. And then in that data set, you have both so the features or the input data and the corresponding label. So corresponding label means whether, sorry, if it is a network intrusion detection system, which we are studying, then the corresponding label could be attack or non-attack, and input data could be the traffic that we are capturing. And during the test phase, what you have is only input data, so only the traffic data. And what you want to do is you want to use this model and you want to feed this model with this input data and expect that it will give you the label, so whether it is an attack or no attack. Okay, so we talked about that this model will also be stored somewhere, and therefore there could be different attacks that could be launched on these type of machine learning based models. And adversarial ML refers to this broad area. And then we looked into attack 1, which was referred to as model stealing. So we talked about that. If a model is stored and if there is a way to give input to this model and obtain the corresponding label, attack or no attack, then it is possible to learn about this model, and that is what is called model stealing. And then we talked about another attack, and this model stealing is actually referred to the stealing the data out of the stored model. Then the second attack that we discussed about was probably misclassification. So you have this model and then you somehow craft the input, and you are actually working in the test phase or operation phase. And so you craft an input so that this model gives you a wrong label. So whatever was an expected label, so that expected label is not seen, but you see something which is not expected. So today what we are going to see is the third attack, which is on the training phase. So which is called a training set poisoning attack. So this is what we are going to study today. So what I want to highlight is that I wanted to talk about one specific attack on each of the different aspects of machine learning models, but I will go into the details of this training set poisoning attack, and you will see what I mean by saying training set poisoning. Okay, so I will be going into the detail of this training set poisoning in a particular context, and this context is about detecting attacks on automobiles. Okay, so any quick question about what we are going to discuss or what we discussed previously? Okay, so yes, so now we are going to talk about vehicle security, and there we will talk about training set poisoning. So in vehicles, so these days the vehicles are the different components of the vehicle, whether it is brakes or whether it is related to steering or whether it is related to doors, everything is controlled electronically. And therefore, there is an electronic control unit, ECU, corresponding to each of these components in the vehicle. So body ECU might be referring to something which is locking, unlocking the doors, or other things which are being controlled electronically. So probably just the windows or other things related to the structure of the car. And then the brake ECU corresponds to the electronic control unit, which is controlling the brake. Then the engine one, again, so engine's speed and other aspects of engine are being controlled electronically, and there could be an electronic control unit for that. So all these electronic control units, they communicate over a bus. Okay, so bus is just a twisted wire where the data is being communicated. And then all of this, there is also a way to access this CAN bus remotely, and an attacker could actually try to compromise that remote connection to gain access to the bus. And if the attacker could get access to the bus, then what it could do is it could start to send malicious messages. So it will try to do impersonation attacks, and it will, let's say, try to impersonate the brake ECU and then send a message saying engage the brake, and then the brake will get engaged. So the attacker could do all these kind of attacks, but then the best way to prevent such attacks could have been that we implement what we have been studying is authentication. So if we could have a message authentication code for each of the messages, then it will not be possible for an attacker to impersonate somebody. So we have studied all these things, that how we could prevent these kind of impersonation attacks or man-in-the-middle attacks by using this idea of authentication and message integrity. But in vehicles, these electronic control units, they are not significantly energy, so they don't have significant energy to utilize these cryptographic algorithms, and therefore what has been proposed as a defense for the in-vehicular network is that let's use an intrusion detection system, IDS, which will actually monitor the traffic on the in-vehicular network, the controller area network, CAN bus, and then it will, by looking at the traffic, it will try to identify whether there is an attack or no attack. So by that we mean that there could be two transmitters for a message. So let's say there is a message corresponding to a brake saying that engage brake. So that message could come from the brake ECU. Okay, so that would be the benign message. So that brake ECU might send this message that engage the brake. But the attacker could also send that message, engage the brake. And then the goal of intrusion detection system is to figure out whether the message is being sent by the attacker or whether the message is sent by the actual brake ECU. So it is just trying to, intrusion detection system is trying to see to differentiate between this benign and the adversarial behavior. And if it definitely identifies the adversarial behavior, then it will raise an alarm. So is this environment clear where we are trying to operate this intrusion detection system?
Sir?
Yes.
Sir, this machine learning based system?
Yes, so all intrusion detection systems are typically machine learning based, yes.
So to train this system, how do we get the data where such attacks are there? Like there will be a lot of data where there is no attack, but there will be very little data where there is an attack.
So you could generate the data as well. So you can try to say that I have attached an attacker to the bus, and then you let the attacker send these malicious messages by impersonating one of the ECUs, and then you collect the data, and that becomes the data which you could utilize to train the intrusion detection system.
Right, sir. Right. Yeah. Thank you, sir.
Okay. So there has been a lot of research in development of these intrusion detection systems, And one of the best performing intrusion detection system for this in-vehicular networks are called voltage fingerprint based intrusion detection system, so WITS. So what this WITS does is, so it looks into, so I said that the canvas is a twisted wire, and on that twisted wire what happens is that these bits are communicated, and then a packet is communicated in terms of the bits, and these bits are represented in terms of voltage values on the twisted wire. So this figure is actually trying to demonstrate the voltage value. Okay, so if you have an ECU1, so let's say this ECU1 is the brake ECU, and it is trying to send a packet on the network. So this packet will contain bits, and those bits will be represented by the voltage values that will be sent on the bus. So if you see this black line here, so you see that the voltage values that the ECU1 will induce on the network will follow this distribution. Okay, so the black lines distribution. Okay, and then let's say this ECU2 is corresponding to the engine. Okay, so if this ECU2 is referred to that engine ECU, and then it is also trying to send packets which are being sent as bits, and then which are being represented on the bus as voltage values. So then that follows this green curve. And the difference between this black and the green and then the other colored curve is that although they are trying to send a voltage value of 2 volt, that is the way in which the communication should have ideally happened. But when they try to push this 2 volt, they are not able to send the exact 2 volt on the bus. So there is always some difference, and this difference comes because of multiple factors. First is their hardware. So every hardware is unique, and so in the hardware to generate the voltages to send the bits on the bus, and then their location. Okay, so if we are monitoring this at a certain location on the network, then whatever voltage is being pushed very close to that monitoring location, there the voltage value will be higher. But if this is the place where you are monitoring and this is the wire, and let's say this ECU2 is here, so you will see a higher voltage for corresponding to the ECU2. You will see a higher voltage. But if this ECU1 is at a slightly more distant location, so remember this is a wired communication here, and they are trying to inject voltage values for communication. So the ECU1 may have a little lower voltage, and that is what is being represented here, that these voltages will be slightly different for these different ECUs. And therefore what you will see that if you try to plot their voltage profile at different times, then you could see this almost Gaussian distribution of voltage values. Okay, so once do you understand from where this distribution is coming and what I am trying to represent here by these voltages? So this is the representation of the physical layer in which these bits are being communicated. So at the physical layer there has to be some medium. So in wireless it is RF communication. In the wired, typically it is there are different ways, but typically it is the voltage amplitude values which are varied in order to communicate bits. And in this case, the voltage value that is varied is around 2 volt, and therefore on the x-axis we are showing these voltage values which are ranging from some values, but basically, and in an ideal scenario you would have seen a spike at 2 volt, but you do not see a spike, you see a distribution because of many factors, hardware distortions, so the distortions related to the amplifier which actually changes the bits into the voltage, and the locations as well. The location of the ECU also plays a role, and therefore you see the distribution. So is this distribution part clear to everyone? Know what is this voltage value and what this distribution is about? Okay, so now that we have this distribution, then what we do is, so this is the data input. So what we also discussed in the previous lecture is that now we have to extract some features and then we will utilize some machine learning algorithm. So what features we could extract? So the features in this case could be mean. So you could just try to calculate the mean of this distribution. Probably that mean will be somewhere around 2 volt, 2.1 volt or 1.9 volt, something like that. So mean, and then you will also try to calculate the standard deviation, variance, skewness, kurtosis, root mean square, maximum, and energy. So these could be different features that you could try to extract. And then it is also possible to extract these features in the time domain. And it is also possible to do an FFT of this distribution and calculate the features in the frequency domain. So you have a lot of features that you could extract from this distribution. And once you have features, then you could utilize any machine learning techniques. So for instance, SVMs, and try to what the goal, the classification here, and is basically an identification. So who is the transmitter of a particular packet? So when a particular packet will be transmitted on the bus, so these packet will have the voltage values, and then those voltage values will be monitored, and that becomes the input, and then this voltage values will be processed. So you see this way to extract the features. So you see the mathematical expressions to extract the features. So you will extract the features from those voltage values, and then you will have you will feed these features to the model. So during the training phase, you will feed these features to the model, and you know who the transmitter is. So in the training phase, you know who the transmitter is. So you know the labels. So in this case, we have 3 labels: ECU1, ECU2, ECU3, and we extract the features and then train our model to identify these 3 ECUs. And during the operation phase, once this IDS looks over a packet, extracts the voltage from the packet, extracts the features out of those voltage values, and then it tries to identify who is the transmitter of that packet. Okay, so basically we are trying to do transmitter identification. Okay, so we are of course doing classification, but the ultimate goal is to identify the transmitter. So is this part clear what we are trying to do using this IDS? Okay, so can someone tell me now how can we detect an attacker in this scenario if we have done this type of, if we have trained this type of intrusion detection system? How can we identify an attacker?
We can monitor the communication, and based upon this distribution, we can see whether a particular message is come from that. What is the chances that it comes from a respective ECU? If that message belongs to that ECU,
yes.
What is the chances of belonging to that ECU?
Good, very nice. Yes, very nice. Anyone else would like to add? Yes, so basically you are trying to see whether whether the features that you are extracting from the packet that is being communicated, it actually belongs to the sender who is claiming to be the sender of that packet. So remember, you do not have any message authentication codes or any digital signatures here, and therefore we are using this intrusion detection system to detect who is the sender of that particular packet. Okay. Okay, so of course this WITS needs regular retraining. So without retraining, you can or training, you cannot detect these senders, and it has to be retrained very often because these voltage features, they depend on many factors. As I said, hardware is one of them, and these features, because of this dependence, these features also change over time. So if the system or if the car gets heated after running for some time, then these features shift slightly, so change slightly because the hardware gets heated up. And if you are starting the car, at that point the features might be slightly different, and after the car runs for a few seconds, then the features stabilize. And so therefore you need to do this retraining, probably in order to cover the effect of temperature changes throughout the day. Even so, even in the morning the temperature will be low, so the features will be slightly different. During noon the temperature will be very high, so the features will be slightly different. So therefore this retraining needs to be done very quickly in order to ensure that you get high accuracy. Okay, so so now we are going to talk about what is the way in which people were using this intrusion detection system earlier. Okay, so not earlier, but even now. So this is the standard way in which typical machine learning algorithms are utilized. Okay, so this is just a typical way that you have trained a model and then you try to identify the attacker. Okay, so this is the typical way, and this is also something that was done earlier. So you had so in this model in prior art, what we had was these different entities. So let's say the engine ECU is the victim in this case, and there is a telematics control unit. It's a compromised telematics control unit which can be remotely accessed. So you see that this term telematics, this means that you could stream video through this electronic control unit. So it has this wireless connectivity. You can, so the Bluetooth connectivity to the car happens through this telematics control unit, or any cellular connectivity happens through this telematics control unit. So there is a remote connection available. So if there is a vulnerability in Bluetooth, then that vulnerability could be exploited to compromise this telematics control unit. And once this telematics control unit is compromised using the Bluetooth vulnerability, then what the attacker could do is it can take control of this TCU as a bot, and then it will ask this TCU to send a message corresponding to engine. So let's say that increase the engine speed. Okay, so that message should have come from the engine ECU, but if this TCU starts to send that message, then it is an anomaly. So then that is something that is being, so this means that the TCU is being controlled by an attacker and it is trying to send those messages. Okay, and then we have this third entity, which is the WITS, voltage-based intrusion detection system, and that is our defense. So the victim is trying to send messages and the attacker is trying to send messages, and the defense has to differentiate between whether a packet is coming from the victim, the actual sender, or it is coming from the attacker. So this is the typical way in which machine learning algorithms are utilized. Okay, so of course, if as I have been saying that the attacker's voltage features, or any ECU's voltage features for that matter, depends on different factors, for instance the hardware and the location. So if we assume that even if the attacker could take control of a telematics control remotely, it can only compromise its software. So it cannot compromise its hardware remotely. So it cannot alter with the hardware. The hardware will remain the same, and therefore the voltage characteristics may not change. Also, the location where this TCU is connected, that cannot change. So in that case also the voltage features should remain the same. So what the attacker could at best do is probably try to heat or cool itself in order to change the voltage feature. So that is the only thing that the attacker could do. And therefore these voltage based intrusion detection system work with around more than 99% accuracy in detecting attacks. Okay, because there is, for the attacker, there is no way to change its voltage features. Okay, so this conventional model of detecting attacks clear to everyone? Okay. Okay, so what we thought was that we should think it in terms of more powerful adversary. Okay, so we should definitely not limit ourselves to this conventional way of detecting attack. And therefore we considered that this is a bus. Okay, so bus controller area network bus, and there is always a possibility that there are more than one attacker connected at different locations on the bus. Okay, so bus means just a twisted wire, and that wire moves throughout the car connecting different components. It is at the front connecting the front lights, and then it is also on the back connecting the back lights, or the trunk is also controlled using the same wire. So this is the same wire which is running throughout the car, and it is connecting many systems, and therefore it is always possible that not one but there could be two compromised attackers connected to the same wire. So what we said that, okay, so we had this engine as the victim and WITS as the defense, and this TCU as the attacker, but there is one other ECU which is now compromised, and we call this second compromised ECU as accomplice. So there are two adversaries. The first adversary is called attacker and the second adversary is called accomplice. So there are now two adversaries connected to the bus. And then we come up with an attack which we call duet. And this attack actually follows this idea of training set poisoning, where and this is and I will tell you what we actually do in the training set poisoning attack. But basically, as the name suggests, when there is this training or retraining happening for this intrusion detection system, we corrupt the training data. So the data from which the intrusion detection system is learning what is a benign ECU and what is an attacker ECU. So we corrupt that data, and after corrupting that data, after poisoning that data, we show that if the attacker launches an attack impersonating, let's say in this case, engine, then the intrusion detection system will not detect that attack. Okay, so I will talk about this in more detail, but at least is the approach clear to everyone? So what is the approach here? So the approach is that the conventional intrusion detection systems follow machine learning algorithm, and therefore we should think of how can an adversarial ML approach bypass the intrusion detection by intrusion by this IDS. But then in order to implement or realize this adversarial machine learning approach, which is in this case training set poisoning. So we looked into what we could do, and then we found that we could do training set poisoning attack. But in order to do that, we need two attackers, and we justify that it is always possible to have two adversaries connected to the bus. Okay, so is that logic clear to everyone?
Yes.
Okay. Okay, so now let's look into the same figure, ECU1, ECU2, ECU3. Okay. Okay. So if you go ahead and plot the voltage distribution of the three ECUs, so victim, attacker, and accomplice. So remember, attacker and accomplice are also the some of the electronic control units connected to the same bus. So they will also have some voltage features, and we could always go ahead and plot or extract features out of those ECUs as well. So rather than saying ECU1, ECU2, ECU3, now we are calling them victim, attacker, and accomplice. Okay, so in this scenario, so let me quickly ask you this question, that if the attacker impersonates the victim and sends a packet that should have been sent by the victim, whether our WITS would detect the attack or not. So if this is the scenario, that these are the three labels that the intrusion detection system has utilized during training, and now it is in the operation phase and it is trying to see whether a packet has been transmitted by a victim or an attacker. So if the attacker tries to impersonate victim, will it be able to will the IDS be able to detect the attack?
Sir, if the distribution are different, like it will be able to detect. Like,
Yes, so the distribution is definitely different. So here you see that the green curve is definitely different than the black curve.
different.
Yes, you are right that if the distributions are different, let's say significantly different, and in this case it is significantly different, then it is possible to detect the attack. So that's correct. What about accomplice? So if the accomplice is also an adversary, and if it tries to impersonate, what happens in that case?
It will be difficult.
Yes, it will be relatively difficult, but it will definitely work, because some features might be different. So probably in the case of victim and attacker, probably just the mean feature could be the one of the most prominent one, and just by looking at the mean, it is possible to differentiate between the attacker and victim. But in the case of accomplice, to differentiate between accomplice and victim, probably mean may not be a good feature to differentiate, but there will be some feature, probably variance.
Standard deviation.
Yeah, standard deviation, that feature could be an important one to differentiate between two, but some feature will work out. Okay, good. So this unimodal Gaussian, and unimodal means one mode. So there is just one bell here. Okay. So yeah, so this will work fine. Okay. So remember that we are talking about the fingerprint corresponding to each ECU. So one single ECU's distribution is shown here. Okay, so what we did. So we wanted to first figure out a way to probably let the intrusion detection system learn from some malicious data set, but we have to create that malicious data set. And in order to create that malicious data set, we had to do something. So remember, I showed you in the last class this stop image, the traffic light, traffic sign image of a stop. So the adversary had to paint some letters on that stop image in order to fool the machine learning algorithm that is utilized by an automobile. So here we also have to create some malicious data set. Okay, and in order to create that malicious data set, what we did was, and I also said that just one individual ECU cannot change its voltage fingerprints because there are hardware restrictions. Okay, so what we did was we utilized not one so what we did was which was very interesting, is that when the victim is transmitting, okay, so when the victim is transmitting its packet, so then what the attacker could also go ahead and start transmitting something on the bus. Okay, so the bus is a broadcast medium on which anyone could transmit under certain restrictions. So, but we found that it is possible to bypass certain restrictions, and it is possible for the attacker to transmit at the same time when the victim is transmitting. Okay, so when the victim is transmitting, let's say so this is on the y-axis we have the voltage. Okay, so on the y-axis we have the voltage, on the x-axis we have time. Okay, so the victim would start transmitting. It will transmit 0 volt, then it might transport 2 volt, then it might transport 0 volt, and then 2 volt to for some time, and then 0. So this is just the way bits are being communicated. And then now at one point, what the attacker would start doing is the attacker will also start to transmit its own signal. Okay, so it will also start to transmit something. So if the victim and the attacker, they both start to inject voltages on the bus, what will happen is that the total voltage that the intrusion detection system will see will be higher. Okay, so earlier if it was 2 volt, it will be probably 2.2 volt, or so what we are looking at is the distribution, not the exact voltage at a particular time, but at a particular, even at a particular time, the voltages will be higher. And that is what we are showing by the distribution here. So the 3 curves you already saw, but now you see that for this victim plus attacker curve, this dotted curve here, so this curve here, we have 2 modes. So one mode is for the benign samples and the second mode is for the corrupted samples. So which means that the samples where there is no overlap, so the victim samples where there is no overlap with the attacker samples, the voltage values will remain very similar to the victim's voltage values. But where there will be an overlap between the attacker's voltage and the victim's voltage, the corrupted samples will have higher voltage. Okay, so on the x-axis we are plotting voltage values here. So here you see that it is around 2.15 volt. Okay, so the corrupted voltages will have higher voltages. So this is the way we found to actually create a malicious data set. Okay, so I will tell you what happens next, but at least how we created this malicious data, is that clear? So when the victim was transmitting, the attacker was transmitting, and because of this overlap, some data was corrupted, and the voltage features got corrupted. So you see the distribution got corrupted. So is that part clear, how we are corrupting the voltage features of the victim?
Sir, here by introducing this corruption, so are you trying to shift the original benign distribution so that it fits the malicious?
Yes, so we are trying to change the distribution or voltage distribution of the victim. Okay, so basically that is the goal. Shifting is just another way of saying it, but we are not trying to shift it towards something. We are just trying to change it to something else. So that is the goal. So we are just trying to change it to something else. So the victim's benign distribution, benign fingerprint, is getting changed into some different fingerprint. Okay, so think about
which is easy to attack.
Yes, which is easy to attack. Exactly. So I will go to that. So which is easy to attack. So that is correct. So if you see the mean, if you just want to see the mean of this victim, you will see the black curve. The mean will be different. And if you see the mean of victim plus attacker, that the mean will be different. The mean value probably will be somewhere here 2 point something. Okay, so the mean is a feature, and that feature has changed. Similarly, other features would have also changed, especially the standard deviation would have changed. So that is correct. So that is what our goal is going to be, to alter it so that it is easier to attack. Okay. Okay, so now we move to the next step, and where we have, so this is the training set fingerprint now. Okay, so when the victim was sending, the attacker started transmitting, and what the intrusion detection system learned was a malicious fingerprint of the victim. Okay, so in the benign environment, the idea should have learned the black curve, but what we have been able to do is, now this red dotted curve was the one that the intrusion system learned about the victim. Okay, so now that the intrusion detection system has been fooled to learn the malicious data set. So this was the training set poisoning. So we have poisoned the training set. So what will be now the attack? So during the operation phase or the test set, what we will do is, so the accomplice will start transmitting, accomplice will impersonate victim and start transmitting a packet which should have been sent by the victim. So accomplice is the actual adversary. And what the attacker is doing very similar thing. So attacker starts to transmit whenever this accomplice is transmitting. And then there is an overlap of voltages, and you see the blue curve, probably, yeah, so blue curve is difficult to see. So let me, okay. And should I delete it? Okay. Okay. So now you see this blue curve, which is the accomplice plus attacker. And you see this blue curve now matches very closely with the red dotted curve. Okay, so victim plus attacker was the result of training set data poisoning. And then we come to the operation phase, where or the test phase, where the accomplice is impersonating the victim and the attacker is again assisting the accomplice, and it starts transmitting when the accomplice is transmitting. And then you see that the voltage distribution of accomplice plus attacker is very close to the voltage distribution of victim plus attacker, and therefore the intrusion detection system will not differentiate between a packet which is sent by which has the voltage features of accomplice plus attacker, and which has the voltage features of victim plus attacker. So that differentiation is very difficult to make because of the closeness of the distribution that you see. So those two distributions are very close, if you could see it. So now we can say that if the accomplice impersonates the victim and the attacker helps the accomplice, then the accomplice will be able to bypass detection by the intrusion detection system. So is this clear to everyone? What happened at the end? So what is the training set poisoning, and then what happened during the operation phase? Any question?
Sir,
okay, yes, please go ahead.
Sir, sir, this ECUs. So, sir, is brake is an ECU, right?
This ECU is?
Like suppose these ECUs are components of the vehicle, right? And,
yes.
I mean, brakes and gears are also ECUs. So,
Yes.
So suppose if the driver of the car changes, suppose that like I bought a car and like I sold it after 3-4 years. So there is another driver. So the way the driver drives, like it will affect the distribution of the voltage, right?
No, so this is so yeah. So let me first clearly say that the driver's behavior does not affect ECU's behavior. So these voltage features are actually electrical features, and they are dependent on the electrical circuitry, and therefore it depends on the hardware of those electronic units or their location corresponding to where they are being, the voltage values are being monitored. So these are some of the things which affect, but not the driver. But then let me go one step extra and say that the features like the way someone turns a vehicle on a turn or someone presses a brake. So the sequence of packets. So that is what is the pattern here. So how the brake is being pressed will be represented by a sequence of packets. So the brake look, if the packet contains the location of the brake, and let's say it is being refreshed every 1 millisecond. So location of the brake is being refreshed 1 millisecond. And then if you see that location of the brake and you try to plot the way the brake is pressed by a particular driver, and then you create a profile for another driver. So those two profiles will be different. Similarly, somebody, the way somebody accelerates, that profile will be different. The somebody turns, that profile will be different. So all those things will be different. And yeah, you could do driver identification using those profiles. People have looked into that aspect.
Thank you.
Okay. Okay, so let me just quickly ask, so would this attack be still possible if the attacker impersonated and the accomplice started transmitting when the attacker was transmitting? Would the attack be still successful? So can someone try to answer that question? So the attacker is now impersonating the victim and accomplice is assisting. Because so okay, so let me first also add some clarification. So during the training phase, the attacker actually adds the malicious voltages to the victim's transmission. But so that is, and then during in the current scenario, accomplice is actually impersonating and attacker is assisting. Now what I'm asking is that if the training set poisoning happened with the help of attacker, but then during the test phase, the attacker tries to impersonate and accomplice tries to help. So this accomplice plus attacker is actually attacker plus accomplice. So would the combination also work? So this is this commutative? Can someone try to make a guess at least? No guess?
Sir, if you could repeat the question again.
Okay, so what I'm saying is that during the training phase, the victim's voltage samples were corrupted by the attacker. Okay, so that happened during the adversarial the attack part where we are trying to do this training set poisoning. So the attacker actually corrupts the voltage values of the victim. So during the training phase, but during the operation phase, rather so during the operation phase, the attacker impersonates the victim. So which means the attacker transmits the packet impersonating the victim, and then the accomplice adds tries to transmit at the same time and then tries to add some voltages to the attacker's transmission. So will the attacker plus accomplice scenario, so the attacker plus accomplice scenario, will this still be able to bypass the the detection by intrusion detection system.
Shouldn't it be two different things? It should.
Yes. Yes, that is correct. So it should be, these are two different things. So when I'm showing you this plus sign, it is not actually a plus sign here. So ML algorithms are able to differentiate even if there is some significant difference in the distribution. And if during the training phase, if the attacker is the one which actually added its voltage samples to the victim's sample, then during the test phase, it should again be the attacker which should add its voltage samples while the accomplice is transmitting. So only then it is possible to bypass the intrusion detection system. Otherwise, this will not work. So we tested it, and yeah, it did not work in that way. Okay, good. So machine learning models are definitely very powerful, but yeah, you could always come up with some ways to bypass them, but not many different ways. Okay, so let me just quickly show you what happens in the feature space. Okay, so we plotted the different features. So mean, variance, skewness, and kurtosis. So if we plot these three features of victim, attacker, accomplice, so you see that for the mean, this attacker's mean is high, accomplice's mean is low, and then victim's mean is somewhere in the middle, and then their variances are very, very close. So probably variance is not a good feature to differentiate them. But again, skewness is a good feature to differentiate between those three. And then kurtosis, it is also a decently good feature to differentiate between them. So if we use this different set, and if there is this benign environment where there is no training set poisoning, then we could have the intrusion system could have easily identified an attacker if it tried to impersonate the victim. But what happened when the victim plus attacker was introduced during the training set poisoning attack? So its features changed. So the star value, so you see that the mean value increased, the variance value also increased, skewness value increased, and kurtosis got decreased. And then the accomplice plus attacker, you see that all those features are very, very close. Okay, so this skewness is slightly different, but other than that, all the other features are very, very close. And therefore, an ML model which is trained with this data set is not able to differentiate between victim plus attacker and accomplice plus attacker, and therefore accomplice is able to impersonate the victim. So is this hopefully this impact on features figure is now clarifying the aspect in more detail. Any question about this impact on features? Impact of this training set poisoning on features specifically? Okay. Okay, so let me quickly ask you an easy question to see if you are with me. So what is what is the part where training set poisoning is happening? So what so can you tell me the feature value of the aspect where the training set poisoning is happening? Okay, so what is the label here corresponding to, out of these 5 labels, which label corresponds to the training set poisoning?
Red star.
Yes, the red star. So victim plus attacker. So we are trying to make sure that intrusion detection systems learn malicious fingerprint of the victim, and that is what training set poisoning is about. Okay, good. And then in order to bypass or lead the intrusion system to misclassify or not able to detect the attack, is being done by this label accomplice plus attacker, and this happens during the operation phase or the test phase. Okay, so so we also demonstrated it on a real vehicle, and so you see here we have the dashboard of a real car, and we added some circuitry to the car's network. So some of these things are added, and then we have an oscilloscope to monitor the voltage values and then collect the voltage values. And then we have a few terminals open here. So 3 terminals. So one is looking at the traffic, and then the second one is looking into some logs, and then the attacker. So this is the attacker log, and then the third one is the IDS log. Okay, and we showed that this does not work. So what we needed was a real car and some connectors, some Arduino boards, an oscilloscope, and of course we did a lot of reverse engineering here, and then we needed to understand how communication happens on the in-vehicular network. So a lot of understanding of the protocol, and then of course we needed to understand how the intelligent systems work. So of course knowledge of machine learning was needed. So let me quickly show you this video. So you see that what we are trying to do is first you see that it is 700 revolutions per minute. Okay, so that is the RPM for this car. So this car is stationary, and what we are trying to do is we are trying to see the bit values, so the packets that are being communicated corresponding to the RPM meter. So these are the only that is the traffic. So we are just filtering that traffic and showing that traffic on this log here. And in the first part, so let me just slightly go back. So in the first part, what we are trying to do is, so the attacker is starting the voltage fingerprint manipulation. So it has started doing training set poisoning attack, and the intelligent system is in the learning phase. So it is trying to learn the fingerprint of all the different ECUs which are connected to the bus. Okay, so in that phase you still see 700 revolutions per minute. So no visible change is shown during the first part of the attack, the training set poisoning part. And now the attack actually starts, and you see that the RPM is now 7,000 revolutions per minute on the car. So this meter is showing 7 here, and the attacker is of course launching attack, but the intelligent system is not raising any alarm. And the reason is that now intelligent system has been tricked to learn the wrong fingerprint of the victim. But yeah, so basically this is a nice demonstration to show that this attack works against this intelligent system. Okay, any question about this small demonstration? So what the attacker in this case, and the attacker has these Arduino boards which are connected to the bus. So these Arduino boards are actually sending messages corresponding to the RPM meter, and then this RPM meter is taking these packets. So it should not have if there was some digital signature or message authentication codes, of course this RPM meter would not have understood or at least processed the packets which are being sent by these Arduino boards on the network. But because there is no security, no authentication, they do accept these messages. So that is something that has been shown 10 years ago by different people, that these RPM meters will accept any packet received by them if that packet is in the correct format. But then people have been working on these intrusion detection systems which detect such attack. So if you could not prevent the attack, you have to go ahead and detect the attack. And what we showed was that even these intrusion detection system may not detect the attack if you do the attack intelligently. In this case, following the idea of adversarial machine learning, following the idea of training set poisoning. Okay, is this any question related to this?
So during the creation of adversarial samples, it basically changed the voltage of benign samples significantly. So shouldn't the retraining should not be done on such samples? Shouldn't such kind of defenses put in the car, or is it in the range of the normal signals?
Yes, very nice. So that is an excellent question, Sanchit. So definitely. So if you have a defense which could detect that even during the training, the voltage values that I am encountering is very different than what I was encountering in the previous training. So if two training data sample sets could be compared in a defense, then definitely this attack could be detected. And we actually took some care of that in our paper. So what we discussed was that we will change the fingerprint very slowly. So we will not change it. What you saw in this figure was a drastic change, but the way we actually showed in our paper was that we will change the fingerprint slowly. So the second mode that you saw in that figure, that will start becoming prominent very slowly over multiple training phases. So as I said, the retraining should happen very quickly, and therefore there will be multiple training phases even within a day, and we could change those features slowly over those multiple training phases. So definitely, so that is an excellent question, Sanjit. Okay, good. So you show a very nice work related to training set poisoning. So I definitely would like to go into many more adversarial attacks, but in the interest of time, I will move ahead to our next topic of firewall. And I will, so as I said, I will try to find some other ways in which I could provide you some decent reading material about adversarial machine learning. But for now, I will share that book link that I have found. So typically you follow a new research topic by reading papers, but I understand that reading papers is going to be very difficult for many of you, and therefore yeah, please go through that book. Hopefully it will be easier, but yeah, many of these books are also not very easy to follow. So yeah, I guess again in the major exam, I will not ask anything which I have not covered in the lecture. So just read these books or any other material online, considering that fact that whatever I have covered in the lecture, I will ask only that in the major exam. Okay, so thank you. I will see you on Friday then, and we will talk about firewalls. Okay, bye bye.
Thank you, sir.